Should we start?
Yeah, I was thinking I might as well just get started now. Um, Share my screen. Okay. Okay, so once again, I'm Irene. This is the workshop on solving differential equations on computers. Um, I will paste materials in chat again. So this is the command to git clone the repo where all the materials for this workshop are located. It's the same one as last time, so if you've already done that, you can just git pull to get the new stuff. So starting here, most of the stuff is in a Jupyter notebook. So once again, you can start a session interactively with the on-demand website. Starting a job will look like this. You can just use an environment module, the most recent version of Python. Standby queue, wall time of however many hours you need. And then you can just click launch to do that. I will just use the one connect to Jupyter that I already have open, which will give us a screen that looks a bit like this. So navigating to this subfolder, DiffyQ Workshop. This one will be the one that we are mostly working from today. Before I do that, I will briefly recap the major points from last time that are the most critical to understanding what I'm going to be talking about today. So the basic idea is that differential equations, we're going to be looking at how the variables that we want to study are changing over time, and also how they change throughout space at a given point in time. So the general scheme that we'll use to solve these equations on the computer will start from breaking up the computational domain, the extent of our system, into a grid of cells. And then we will be sampling the various quantities that we that we care about. I'll also be calling them grid functions at some points. We'll be sampling them within those cells. And then we will start stepping forward through time. So within each time step, within each discrete chunk of time, we will be using the evolution differential equations to estimate how much a given quantity is changing during that period of time. And then we will add that onto the variable for the next time step. And then we will go out to the boundaries of our grid, the outer extent, and we'll apply boundary conditions to ensure that they're very well behaved, that we don't get weird things like waves reflecting off of a boundary in empty space, or making sure that our inlets and outlets, if we have flow in our system, are behaving appropriately. Okay, so, right. We will now pivot and we'll give ourselves a little bit of background on the general relativity, because we're going to be trying to solve the equations from that field today. So around the turn of the 20th century, physics was starting to run into problems. Various experiments were disagreeing with theory, and it was becoming apparent that it wasn't experimental error that was causing those problems. So one major thing that was starting to come up was the propagation of light. So to this point, physicists had hypothesized that light should propagate through some medium known as the luminiferous ether. However, Michelson and Morley set up an experiment to try and detect this ether by measuring small differences in the speed of light at different points in the Earth's orbit around the sun. So the idea is that when we're moving away from some different star, we should be able to detect that the light from that star is moving a little bit slower than it would be if we were moving towards that star as the Earth goes around the sun. However, when they actually carried out this experiment, they found, much to their surprise, that the speed of light always remained constant, the speed of light in a vacuum to be precise. So Albert Einstein followed this realization to its logical conclusion, which led us to the startling idea that if the speed of light in a vacuum is always constant, then the flow of time and the distances between points that were thought to be fixed cannot remain constant, and instead they depend on the speed that the observer is traveling, which leads us to this theory of special relativity, so named because it's a special case of the later general theory of relativity. So the names are a little bit out of order in time, but that's neither here nor there. So this leads us to weird effects like time dilation and length contraction. So if I'm observing a rocket ship moving along at a significant fraction of the speed of light in the distance, I'll also be able to observe that their clocks are ticking more slowly than mine are, and they will also measure the length of their starship to be shorter than I do. So another famous problem that's starting to crop up around this point is known as the precession of the perihelion of Mercury. So astronomers are starting to notice that Mercury, as it is orbiting around the sun, is not exactly where we are predicting it to be. So this is a very small effect, but as they gathered more and more observations, observing it more and more precisely, they're realizing this isn't some observational error. There's something wrong with our model of gravity. So Einstein then seeks to incorporate gravity into this theory of relativity, generalizing that theory. So one critical observation that he made that led to the development of this new relativistic gravity is that if an observer is in a box, they fundamentally cannot tell the difference between that box being in a uniform gravitational field or that box undergoing constant acceleration. So, given that we just discussed that a moving observer has their flow of time change, this tells us that there's also a connection between gravity and time. So basically, we also have a gravitational time dilation separate from the one that's just from going fast. So the deeper into a gravitational field we get, the slower our clocks tick. And in fact, we do see this happen just between the surface of the Earth and low Earth orbit. So a clock on the International Space Station is running a little bit faster than it is at mission control on the Earth. And in fact, this is a very important part of how GPS systems work. They have to keep very careful track of these extremely tiny time differences in order to, and then they correlate those and they're able to work that out into a position on the face of the Earth. So basically, in general relativity, we combine space and time into a single concept that we very cleverly call space-time, which we often will visualize as a sort of four-dimensional fabric that stretches and deforms in response to the distribution of various sources of mass and energy in that space-time. So stars, planets, electromagnetic waves all contribute to this. And in turn, this distorted space-time will affect the paths of objects moving within it. So the common refrain here is matter tells space-time how to bend, and space-time tells matter how to move. A standard demo that we'll do to show this will involve stretching a rubber sheet out, and then we can place a bowling ball on the sheet, and it'll bend that sheet and pulling it down. And then if we take, say, like a golf ball and try to roll that in a straight line on the sheet, instead of going in a straight line, it will travel in a curved path around the bowling ball. So instead of a force in the classical sense, gravity sort of becomes this geometric effect. So in the same way, as an asteroid is approaching the Earth, we'll see that its trajectory is bent around the planet. And less obviously, a famous proof of general relativity, evidence in favor of it, is that we can even see light rays bending around the sun. And this was observed by Dyson and Eddington in 1919 during a solar eclipse. They were able to show that light rays bending around the sun from a distant star essentially shifted the position of that star during the eclipse. So since then, Einstein's theory has been repeatedly verified experimentally over and over and over again. But of course, in order to verify a theory, we must first make predictions with that theory. So in general relativity, we do that by finding solutions to the Einstein field equations. But of course, as was the case with computational fluid dynamics, finding these solutions is easier said than done. There are very few known exact solutions to this set of equations. And as I also mentioned yesterday, these solutions rarely correspond to physically likely or interesting scenarios. So we turn to computational methods to try and solve these equations approximately instead. So I also need to make a quick note on units. The standard convention in general relativity is to use what we call geometrized units. So in this system, we set by definition the speed of light to be equal to 1 and the universal gravitational constant big G to also be 1. So in this system, we're able to, so this leads us to setting, we define the second as 2.998 times 10 to the 8th meters, and a kilogram to 7.426 times 10 to the negative 28 meters. So we're expressing pretty much every single unit of interest in terms of length. And this, I know this sounds weird, but it does make a lot of the work a lot easier. So, when we set these constants to 1, when we do the math, we're no longer carrying around large stacks of constants, which means we're less likely to make a weird error in our algebra somewhere. And then an interesting example that I'm very fond of is that in this system, the mass of the sun is about 1.4 kilometers, and the mass of the Earth is about 4.4 millimeters, which I find makes it a lot more intuitive just how vastly different scales these objects exist on. It's a lot more intuitive than saying something like 10 to the 24 versus 10 to the 30 kilograms. So this also has the added effect of allowing us to express many quantities in the systems that we're examining as multiples of a black hole mass. So, for example, in a simulation, we might just leave the mass of a black hole as some m. And then we can define the masses of other black holes in the system in terms of a ratio to that. So we might have 2m or m over 2. And then we can express the distance between the two black holes, some multiple of that mass, like 50m. And this works because the effects that we're studying are scale invariant. No matter what the value of that big M is, if we place two black holes, each of mass m or of mass 2m and m over 2, 50m apart, the effects that we observe will be the same. to that scale factor. Whether we're talking millimeter mass black holes 50 millimeters apart or 2 kilometer mass black holes 50 kilometers apart. So let's start talking more about how we do these simulations. So as I mentioned, the fundamental thing that we're looking at are the Einstein field equations, and these equations relate the distribution of matter and energy in the universe to some metric tensor that we call G, and we can see here it has subscripted indices. So this is a tensor quantity. These indices run from 0 to 3, which corresponds to the dimensions of time, and then 3 spatial dimensions of our choosing usually. And this describes how space-time is curved by detailing how we would calculate the distance between different points in space and time. So in flat space-time, this reduces to the familiar Pythagorean theorem that we can use to calculate distances. Right, we're trying to numerically integrate these differential equations. And as I mentioned, there's very few exact solutions to these, and those are limited to things like a gravitational wave propagating through empty space or single black holes. So to do this, we're going to be using a very powerful code package known as the Einstein Toolkit, which is itself a part of the Cactus Computational Toolkit. So Cactus itself is made up of individual modules known as thorns, which will provide all the various functionalities that we need. So we have thorns for things like setting up the numerical grid, setting up the initial data, applying boundary conditions, and so on and so forth. And Cactus also provides for us a common interface that will allow these thorns to interact with each other and share data. Here's the toolkit's website, and we also have the gallery. This offers us some example simulations that are interesting. One of note is the gravitational wave event from the binary black hole merger that was first detected on September 14th, 2015. So here we have simulation details, and we can see some of the things that I've mentioned. We can see that in the simulation itself, we don't have specific black hole masses. Instead, we have the black hole mass ratio, and we have the initial separation given in terms of the system's mass. The time to merger is also given in terms of mass as well. Interestingly, the mass of the final black hole is actually slightly less than 1, which is by definition the total mass of the black holes at time 0. So that's because the black hole merger radiated just an incredibly vast amount of energy during the final in-spiral phase. And it also has useful details of the simulation, like the total memory needed, the runtime on the specific hardware they used, as well as a useful submission command. So that tells us if we want to do this ourselves, how many cores would we want to use? How long should we expect this to go for? So, of course, we can't use the usual techniques just yet because, as I mentioned, the usual techniques for numerical integration are assuming that we have a grid of points in space and that the location of those points is some fixed thing and that time will flow uniformly everywhere in our computational domain. But as I also mentioned a little bit ago, that's not how things work in general relativity. So we're going to have to essentially slice up our space-time into layers. So that means that we're going to turn that rank 4 metric tensor into a couple of separate quantities. We'll have the rank 3 metric tensor, gamma, And we can see that this is subscripted with Latin indices I and J instead of the Greek ones mu and nu. So that's just a convention that tells us that these indices will run from 1 to 3, which is 3 spatial dimensions. And then we also introduce new quantities, the shift vector beta, and then we also have the lapse alpha. So these quantities will refer, these define how space and time work at a single point in our grid in between time steps. So in between time steps, the position of a grid cell will be shifted by beta, and the amount of time that elapses is given by the lapse alpha. So I'm going to take a step back and going to give us a little bit of background on the physical problem that I'm about to present. So classically, on Earth, we have a tidal cycle twice per day. And notably, in most places on the Earth, we get the tides occurring twice per day, and that's because so the tides are caused by the moon pulling unequally on the Earth's oceans. So classically in gravity, the force due to gravity decreases as you get farther and farther from the object, in this case the moon, that is creating that pull. So the part of the ocean closest to the moon is pulled more strongly than the bulk of the Earth, which is in turn pulled more strongly than the portion of the ocean farther away. So we get this stretching of the Earth in line with the moon. And this also applies on an even smaller scale to the entirety of the Earth itself. So the Earth itself is squeezed by this very, very, very small but still notable amount. But the Earth is also spinning. So over the course of the day, as the Earth spins, this becomes slightly misaligned. And this allows us, this misalignment means that the moon is going to be exerting a torque on the Earth. And this has the effect of slowing down the Earth's rotation, making the day ever so slightly longer. So day to day, this isn't the sort of thing you notice, but over the course of millions of years, this has a major effect. And we also see other places in the solar system, it's much more dramatic. This constant stretching and squeezing in the Jovian system dramatically warms up the cores of the moons that are closest to Jupiter itself. So on the moon of Io, there's so much heat that there's extreme volcanic activity. Images of the surface of Io that were taken by the Voyager probes are not accurate anymore because the volcanic activity is so intense that the surface is being remodeled all the time. And on Europa, there's enough heat to maintain an entire liquid ocean underneath miles of ice. So, looping back to general relativity, this leads us to an interesting question. If physical bodies can have their angular momentum changed by these tidal effects, can the same thing happen to a black hole? A common gut reaction to this question is to immediately answer no, because as we discussed, these tidal effects are caused by the force of gravity from one object acting with different strengths at different points throughout the physical extent on the other body. And a black hole is considered sort of defined by having all of its mass concentrated at a single point that we call the singularity. However, that concept for tides is only true in classical mechanics. In general relativity, as I mentioned, gravity is more of a geometric effect, a deformation in the fabric of space-time. So when one black hole deforms the space-time around it, it can distort features in the space-time nearby, like the event horizon of another black hole. So this actually gets very extreme when you're looking at a black hole merger. We can see that the event horizons are extremely distorted, eventually forming this two-lobed structure in the first instant after they merge. So this isn't quite as far out there an idea as we might first think. So to answer this, we'll set up a simple experiment. We'll start with two equal mass non-spinning black holes. So another important thing is that when I talk about the spin of a black hole, this is a dimensionless quantity, and it's related to the angular momentum. And it's also, for black holes, it can only exist between the limits of 0 for a non-spinning black hole and 1, which is the extremum there. And so I say it can't go higher than 1, but that's not, strictly speaking, experimentally verified. But if a black hole were to be spinning faster than that, it would violate something known as the cosmic censorship hypothesis, and we would be able to directly observe the singularity at the center of the black hole. And when I say singularity, this is the same singularity for mathematics if you do something like divide by 0. So if we're able to directly observe a divide by 0 in the real world, something has gone horribly wrong and we need to revise all of our physical theories. So in relativity, we are pretty much we hypothesize that it can't go higher than 1. But that 0 to 1 scale is important for interpreting the results that we get later. And then we're going to set these black holes on scattering trajectories. We're going to impart on them some initial momentum that is angled away from the x-axis here by some angle theta that is equal for the two black holes. And we're also setting them some distance d apart. So our goal when we define this momentum vector p is to have a scattering trajectory. So we want to get them as close as we can to get the strongest interaction possible. But we also don't want to let them merge, because then we just have one black hole and we can't answer questions about the angular momentum of a single black hole at a later time. Okay, so we're going to choose the initial separation to be 100 m, because it's important to set these very far apart because of a quirk in how we calculate the initial data.
Marie?
Hmm?
What is the mass ratio between those black holes?
These are equal mass.
They are what? Sorry?
Equal mass.
Equal mass. Okay.
Yeah, so we're trying to set up one of the simplest case to answer our question.
So it's equal mass, so the ratio is 1.
Mm-hmm.
No spin for any of those. No spin, right?
Right.
With a certain angle. So they are attacking, the attack angle is the same.
Right.
Okay, so it's not a direct collision. Okay.
Right.
Oh, okay, I got it.
Yeah. So this is actually, this setup is modifying a common test run for codes, which involves just setting them on that head-on collision course, but we're angling their momenta differently to avoid a merger.
Okay.
Yeah, so a weird thing happens when we try to generate this initial data, though.
But even if you have an angle, they could merge eventually, right?
Yes.
There is a limit. I imagine that there is a limit. There is a minimal angle that prevents the merging.
Yep. I'm actually going to be
the angle is lower than that. There is no way it will merge no matter how.
Yeah, I'm actually going to talk about that in a little bit, how we would go about finding that.
Okay, I'm just trying to follow.
Yeah, okay. So when the toolkit is going to calculate the initial data, it's going to generate the the two initial data, the initial data for the two black holes separately, and then just sort of add them onto a flat space-time. But this doesn't exactly reflect reality, because in reality, the space-time metric is going to include the contributions from their movement from infinite time beforehand. And as I've mentioned several times previously, computers do not like it when you try to throw infinities at them. So what our initial data is actually representing would be, what if we have this universe that is existing and it's completely empty, and then all of a sudden these two black holes pop into existence with their initial momenta. So that's sort of unphysical. Fortunately, the toolkit's evolution equations are programmed in such a way that things are stable, and these inconsistencies will soon be resolved as the simulation advances. This sort of occurs with this unphysical junk gravitational radiation that's emitted and propagates outwards. And as it's unphysical, it can even propagate faster than the speed of light, which is kind of this wacky thing, which is also part of why it's important to make sure that we set our boundary conditions correctly, to make sure that when that junk radiation reaches the edge of our physical domain, it's going to leave the grid instead of reflecting back off of the boundary and wreaking havoc on our simulation. But it is still important to make sure that the simulation does have that time to stabilize, which is why we're setting those black holes so far apart. The example that we're about to go through, I drag this out of my way.
So, well, just okay. Yeah, I'm trying to. So, do you have like a rule of thumb or something for how far away you need to start, because due to that effect, that fake effect of just magically making appear those black holes without history? That the point is that those black holes are just appearing without history, without making any ripples on the space-time, without making any, they just appear there. How far they need to be?
So it's not as much a matter of the distance as the time that's going to occur before we start getting to the strongest interactions between them. So like the merger simulation, the example only has them 10 m apart, but the time to merger is much, much longer than we're going to let this simulation run for.
Okay.
Yeah, so the example that we're going to do here sets the initial coordinate velocities to 0.98. Well, that would be, strictly speaking, that is the relative velocity between them for the head-on case. But that's just how we index it in the file names. And unfortunately, that's one of these cases where the number doesn't represent something observable. That is just sort of this coordinate momentum that gets plugged in to the initial data thorn. And we'll also use an initial angle theta of 0.055 radians. And then the specific momenta that are actually going to get plugged into that thorn are going to just be simple trigonometry from this magnitude and angle, which I'll show you a little more about that in a second. So let's take a look at this parameter file. It's included. Okay, that's unfortunate. Let me reload the terminal real quick. And make sure the cat doesn't step on the keyboard. Also an important thing. So this is in the Diffie workshop subfolder, and then in the shooting black holes folder. So we have this parameter file. All right, one sec. Okay, so we can see that this starts off by activating the thorns that we care about, and I'm only going to mention a couple of these. So ADM base, that is an ML BSSN. These are specific data about the evolution equations themselves. So these are specific formalisms that are related to how exactly we choose to do that slicing up of the space-time. Apparent AH Finder Direct. This calculates the apparent horizons of the black holes, which are a similar concept to the more familiar event horizon that gets talked about in popular science and science fiction all the time, except it's a lot easier to calculate in a numerical scenario like this. Carpet tracker. So that's part of how we're going to work with our resolutions, how we do set up the grid. Space. Carpet IO ASCII, this is an important thing where it offers us outputting specific information from a simulation. So you can see we do things like the quasi-local measures thorn, which will calculate things like the spin of the black hole. So that's an important thing because that's what we're looking to measure. And then it can also output things like the lapse, which is sort of, as I mentioned, related to the gravitational time dilation. Information from the Parent Horizon Finder, which we'll use to examine the trajectories of our black holes in a little bit. Chord base, carpet rigger 2. Okay, so these are super important things. We have so this has the extent of the outermost grid here, as well as the grid spacing of the coarsest refinement level that we use. So this is going to be the coarsest resolution that we work with. And then carpet regrid 2 is going to set up a bunch of nested grids with finer and finer resolutions as we go get closer and closer to the singularities. So here's sort of a figure that shows that really nicely. So we can see here we have the two black holes here and here. And you can see from the color scale, the lapse gets really small near these black holes because time is passing extremely slowly near them. And then we also have the finer resolution near them, and we have coarser grids farther away from them. So this is an important thing we need to do because the values, the grid functions that we care about change a lot near the black holes. And as I talked about, well, on Wednesday, we need that higher resolution near these interesting features in order to fully resolve them and accurately represent them. However, if we tried to do that everywhere, that would take up an incredibly huge amount of memory, and we don't want to do that. So we have the finer grids where we need them and the coarser grids where we can get away with them.
Yeah, I agree.
Mm-hmm.
I miss some. When you say you have multiple grids there.
Mhm.
Those grids are overimposed or they
Yes, they're
replace.
overlapping.
They are overlapping. So you have, let's say, the course, when you mention the course grid, is the course that is in the lower corner, in the lower left corner. So those
Yes.
black, all, so the grid is preserved. You have this coarse grid. On top of that, you have a couple of finer, and after
Mhm.
you have another finer closer to the. So you have one, two, three, four grids. That's
In
what I.
this. Mhm.
And so they are overimposed in the center of or closer to the center of those black holes. All those four grids exist. They are
Yes.
okay.
Um, yeah, so in the code, how this actually is working is
Uh-huh.
that we have the coarsest grid that it is everywhere, not just in these corners here.
That was, I was thinking that was the case, and now you made me realize that.
Yeah.
I was thinking that they were replacing.
N-
That was my understanding from the last time.
so yeah, we do store the data for that everywhere, and
Uh-huh.
then they overlap each other. And then there are thorns that manage the interpolation between those grids, transferring data from the finest to the coarser grids. So, like during a time step, you'll first work on the finest grid and then interpolate data outwards to the next coarser grid, and then do the evolution there, and so on and so forth.
Okay.
Um, so as we go through here, we have the MOL is method of Linesthorn. So that's the specific algorithm that we're using to actually do the numerical integration. Puncture tracker is tracking the punctures, which is sort of jargon for the black holes themselves in this field. Quasi-local measures is measuring things invariant quantities. So as I mentioned, not all of the numbers that we're going to be talking about have observable interpretations, but these local measures, they do. So we try to focus on them as much as possible when we can. Two punctures is the thorn that solves for the specific initial data that we'll be using. It's called the Brandt-Brugman metric. Vial scale 4 is something that will be calculating the information that we would need for gravitational wave analysis if we wanted to do that. So the vial scalars are a set of 5 complex scalars that encode information about the spacetime, and specifically psi4 has information related to the polarizations of the gravitational waveforms. And then the most important things that we care about here are the momenta for the two punctures in the x and y direction. So these are 0 is in the x direction, and then the 1s are in the y direction here, and plus and minus just refer to the two different black holes. So as these x and y, it's just the familiar trigonometry from the magnitude and angle that we have. So then also included is the job submission script. So this is nothing terribly fancy over what Guillermo's been talking about all week. We have the name for the job. We have the resources. This is 4 nodes, 4 cores per node, 55 gigabytes of memory. This is the wall time here is set to a week in minutes. The error and output, the queue. So the interesting thing is that we load the modules, the C compiler, the OpenMPI implementation that we're using, and then the Einstein toolkit itself. And then the other big thing is the actual invocation of the toolkit itself. So we have the MPI run command, and we also have CactusSim is the executable for the toolkit itself, as well as the path to the parameter file that we just looked at. So this is a long job, so I'm going to do the familiar trick from cooking shows. I'm just going to put this in the oven, and then I'm going to pull a cake that I baked previously from off screen. And then that we're not going to look at much more than the opening thing, just to talk a little bit about what the toolkit is doing. So let me talk about the anatomy of a thorn real quick. So here is the folder for a pretty common example of a thorn. Of interest are so here's the source code. So this is all the actual nitty-gritty details about how it's doing what it's supposed to do. There's a scheduling file. This specifies when the code from this thorn should be run relative to the other thorns. And we have the interface file, and this tells us a lot about the data, the various variables that the thorn is using, and provides a common interface for all the thorns to interact with each other and share data. And we also have a parameter file. So when we were messing with that parameter file a little bit ago, the parameters that we were changing were all stored in a file like this. And then looking at the output as the simulation for the black holes runs in the background, it starts out with this clever little ASCII cactus, and then it activates thorns, and then here this is all information about the scheduling of all those thorns, and then it's starting to set up the initial data now. This takes like about an hour alone. When this job finishes, we will get an output directory that is, the name of this directory is going to be the name of the parameter file with a little bit of extra added on, and that's user defined. So now we have a whole mess of text files, and I've included data from this run in the materials for the workshop. So the most interesting things, the ones that we really care about here, are these diagnostics files. So this is the data from the apparent horizon tracker. We also have these MP-Sci4 files. So this is, as I mentioned, related to gravitational waves if we wanted to do that. The L and M here are because this is a spherical harmonic decomposition. The ones that we care about are L2 and M2. And we have these at different radii because if we were to do this analysis, we would need to try to extrapolate this information about the gravitational waves to an observer at infinity. And then we also have these QLM spin files here. The one that we'll specifically look at is the norm2.ascii. So let's look at some of those real quick. So this is the information for the first of our black holes. So we see we have all sorts of information. We have the surface area of the horizon, its extent in the 3 dimensions, various cross-sectional areas. The ones that we really care about here are the centroids. So these will be the position of the center of the black hole in each X, Y, and Z. So if we go back to the notebook, I have plotted these out for us. So we will be using the column 2, time, as well as X and Y positions. Well, okay, so this plot is, time is implicit. But yeah, so this first is the total extent of our, not quite the whole extent of the grid, but the whole extent of the trajectories themselves. So the two black holes start here and here, and then they will zoom in, and they will interact, and then they will scatter off and start escaping towards infinity. And then we can change the axes on this plot real quick to get a closer view, and we can see, so like one black hole is going to come in like this, and we can see that they sort of do this little whirl around each other before they escape. And then we can also take a look at our spin data. So the three columns here are iteration number, coordinate time in the simulation, and then we also have the spin measure of one of the black holes. So I've plotted that information here. So we have time, the time series on the x-axis, and then we have the spin on the y-axis, and then this is the dimensionless spin. It will range between 0 and 1, and it is an invariant quantity. So two observers anywhere in space, no matter what their speeds are, will be able to measure this quantity and agree on it. And then as we see, we do in fact start from 0 spin in our initial data, and then things get really crazy as the black holes are interacting in that strong field regime, where the equations are very nonlinear. And this is sort of the regime where we really need to be using the full form of the equations instead of making approximations, things like classical gravity. And then as the black holes get farther apart, we can see that they've settled down into a new constant non-zero spin, which in this case is about 0.03. So I'm going to briefly pause here for questions, and then we'll take a short break. So do I have any questions right now?
Sure. A quick question.
Yeah.
So the fact that you got at the end something that I was not, I didn't, never, I'm not experienced. I never thought about it. That you get a spin at the end on that is the spin on both black holes or not?
So this
The 0
plot is
0.0.
one of them.
So you will get a different value for the other?
No, it'll be exactly the same because we set up our
Because you
scenario
need,
to be
you
as
need to,
symmetric as possible.
okay. So this 0.03 is a function of the angle. So if the angle changes, you get a different value, or is a function of the momentum of the black hole, or what, or there is something else that makes these values to be 0.03 instead of 0.05 or 6 or whatever.
All of the above.
What is making this 0.03?
So it's all of those factors will play a role. And this particular problem hasn't been studied enough detail that we have like fitted equations to tell us how exactly all of those variables factor into things. But the things that we do know for sure are that as we decrease the angle, the black holes will interact more strongly, and the final spin will be higher. And then, so conservation of angular momentum does apply here. So the angular momentum that we're imparting to these black holes comes from the initial orbital angular momentum that they have, which is going to be a function of their initial um, the initial speed, the angle that that's going at, the distance that they are from each other, all of the normal things that you would classically see going into an angular momentum calculation.
Okay. And those features, those spikes, those are physical. Is that when up to 0.01, it went down to zero, back to zero. That peak, exactly, that peak that is closer to your pointing right now. That is
Yeah.
physical, right? Or is a feature, or is a computational bug or something.
So I do believe that this is physical, but I also think in this case, that this spike up and then back down, I think this, as I recall, this is a function of, it actually briefly goes in the other direction at first, but this is sort of taking the absolute value, which is why it's all positive here.
Okay.
Okay. So is that all you have for now? Or
Yeah, I'm fine.
okay. So if there's no other questions, let's take just a quick break to say 3:05.
Okay.
Okay. Let's start up again. Okay, right. So as we were just talking about with the all those different factors that go into determining what that final spin is going to be. So yeah, this single case is not the end of the story. In answering our first question, we've brought up a lot more. So the two most interesting ones in particular are probably, does this induced spin change as the black holes interact deeper in the strong field regime? That is, as we decrease the shooting angle. And also, does the induced spin change as we impart a different initial velocity to the black holes? So in order to try and examine this, to answer these questions, we actually find a very nice use case for the array job functionality in Slurm. So we'll sort of demonstrate that real quick. So to answer the first question, we might try to set up an array job to try as many different shooting angles theta at the same time as we can. So that'll look like, I've included an example submission script for an array job in the materials for the lesson. So if we take a quick look at that, it's pretty much the same as the one for the single case. The important differences are that we use the array option here. And for this example script, I just have 3 different cases. So the array index that Slurm will iterate over is going to go from 0 to 2. And we also use the bash script functionality of arrays and set up an array of strings. So in this case, there are 3 different angles. And then we will use this array down here in the invocation for Cactus itself. And where we had before, just in plain text, this value for the angle, we instead have a reference to the array that we set up. So we have the name of the array, and then it's indexed with this Slurm variable, Slurm array task ID, which will tell it which. So, when Slurm goes through, it's going to plug each of 0, 1, 2 into this array, get the value of the angle as a string, and then plug it into the file name. So we would want to make sure that when we create these new parameter files, we change the file name accordingly to make sure that we are following this same format. And then when we go to edit our parameter file, the options that we're going to use to change that shooting angle, we're going to be changing these components of the initial momentum, and we're going to be setting those to plus or minus v0/2 times the cosine or sine of theta, according to the initial data schematic that we have here. So v0 in this case is the 0.98 that's in the file name here. And then if we were going to try this at different initial speeds, we would be changing that value as well. So if we do our first batch of angles, we will see pretty clearly that as we decrease the angle at a constant initial speed, we'll get higher final spins. So the next job from there will be to see just how close can we get ourselves. Excuse me 1 second. to that merger regime without actually merging our black holes together. So we might first set up an array that runs over this range of theta, and we'll find that the merger ends up occurring between the 2 points that we submitted somewhere at this big red dot. So then we can then submit further array jobs trying to refine that and getting closer and closer to that merger to get more and more data out of this. So, running just a basic search algorithm. And then we can also try running at different initial boosts. And then if we do that experiment, we'll see in pretty short order that the faster we set them off, the higher final spin we get in that case where we're as close to the merger as possible. So a challenge to anyone who wants to try this, editing that parameter file, if you want to go for a high score as it is. The highest spin that I found for the setup is 0.20, which is pretty intense. That's a fifth of the maximum spin where all physics breaks down. However, from the analysis done on those cases, it's very, very likely that we can get much, much higher spins out of this. So if you were to do that, you would need to be using a value of V naught greater than 1.5. And then you'll need to carry out that search to try and find that merging angle, because that angle where the merger occurs is going to get smaller and smaller as we increase the initial speed. Okay, so we're going to now pivot away from this specific example, and we're going to talk about how we verify our results, how we know that these simulations are even kind of useful. Because the fanciest simulation you could do, no matter how much memory you're throwing at it, how fine the resolution, how many CPU hours you're throwing at it, that's all going to be meaningless unless you can show that your results do in fact get close to reality. So the codes that we've been using have all been robustly tested to make sure that they produce the expected results. And we've been using settings, initial data that we know are going to work pretty well. But let's talk about one particular method that we can use to show that the evolution equations as we program them are doing what they're supposed to. And to do that, we're going to be using one of those exact solutions that I've been mentioning. So it's going to be a simple case, and it's going to be drawn from general relativistic force-free electrodynamics. So a brief aside, stellar remnants. The black holes we've been discussing are one type of black star, or one type of dead star, essentially, where the mass is all concentrated in a singularity, and the gravitational field is so intense that there's, eventually there's some radius where light itself cannot escape from the black hole. But so stars die when they run out of fuel to fuse in their core, because throughout their life, the inward pull of gravity is balanced by the outward pressure from the fusion reactions taking place in the core. But as the star ages, it eventually runs out of hydrogen, and then it starts fusing helium, and then eventually it runs out of helium in the core to fuse, and it starts fusing heavier and heavier elements until eventually the pressure at the core is insufficient to continue the fusion process, and the star dies. So when this happens, the star collapses, And then what happens then is going to depend on the star's mass. So the least massive stars shed their outer layers, leaving behind a planetary nebula, which has nothing to do with planets or nebulas, unfortunately. But they are quite beautiful, in my personal opinion, but I'm extremely biased. And there'll be a white dwarf at its center. So this is the eventual fate of the sun in about 5 billion years. More massive stars will explode violently in a supernova, leaving behind a dense core that's more massive, more dense. So this is what we call a neutron star. And then the most massive stars will be what leaves behind a black hole. So neutron stars sort of lead us naturally into the equations to try and solve them. So when we want to study conducting fluids in general, we'll have to combine Maxwell's equations of electromagnetism with the equations of fluid dynamics, which are the ones that we were talking about on Wednesday. And this gives us a system called magnetohydrodynamics. And these will describe systems like the plasma in stars, magnetospheres, such as what occur when the stellar winds from the sun interact with the Earth's magnetic field, and then also like the interstellar medium as well, described in these equations as well. However, we're going to have to take things a step further if the conducting fluid that we want to study involves either extremely fast speeds or extremely dense objects. So this is going to be what we have to use if we want to describe something like the merger of two neutron stars. So to do this, we have to incorporate the Einstein field equations, which will give us a system that we call general relativistic magnetohydrodynamics, or GRMHD for short. So this is what we need to describe some of the most extreme events in the known universe, like the event on 17, this was detected on August 17th, 2017, when we detected the first neutron star merger simultaneously in gravitational and electromagnetic waves. So we detected a simultaneous gravitational wave event and a gamma ray burst. And then basically every telescope on the planet, and a bunch of them that aren't, all looked at the same area of the sky to look at the gradually dimming remnant left behind by the neutron star merger. So this confirmed a lot of what we knew, or what we theorized about neutron star mergers. So this really brought us into the era of multi-messenger astrophysics. Like a lot of theories about our process, nucleosynthesis, were confirmed. So that explains a lot about where gold comes from. So we're going to consider a special case here of GRMHD, which is general relativistic force-free electrodynamics, or GRFFE for short. So this is the case where the magnetic pressure dominates and the gas pressure can be approximated as about zero. So this will occur in systems with extremely intense gravitational and magnetic fields, like the magnetosphere around a neutron star. So the particular exact solution that we're going to take a look at here is known as the exact Wald solution. So this describes a case where we have a single spinning black hole immersed in a uniform magnetic field. So we might see something similar to this in nature, in like if we have a black hole neutron star binary, we would end up with a spinning black hole in an intense magnetic field that comes from the neutron star. but it'll never be exactly what the scenario where we're going to look at. So the reason we can use this case to show that our code behaves the way we hope it does is that this solution is time independent. So if our code were to work perfectly, as the simulation advances, all of the quantities, all the grid functions in the simulation would stay exactly the same. We wouldn't see the metric change, the magnetic field, the fluid velocity, all of those will stay exactly the same. Naturally, they don't. That's sort of the reality of these approximate solutions that we're solving for with the numerical simulations. They are approximations. So this simulation is going to be very, very similar to the parameter file, at least, is going to be similar to the first one. We'll use a lot of the same thorns. The big differences are just that instead of 2 punctures, we'll be using shifted kerr shield to set up our initial data for a single spinning black hole. And then the solver for the GRFFE equations will be provided by the thorn giraffe because it's cute, really. That's the only reason. GRFFE already has most of the same letters as giraffe. And then the initial data for the GRFFE side of things specifically will be provided by the thorn giraffe food, which is another clever thing because it feeds the giraffe. So like the 2 initial datas, the shifted kerr shield provides the metric things like the 3 metric, the shift vector, the lapse, and then giraffe food is going to be coming up with the initial magnetic field and fluid velocities. So when we run that simulation, the parameter file is currently set up to spit out the average and maximum magnetic fields in the x and z direction. Not y, just because this specific, the exact vault solution is the y component of the magnetic field is precisely 0. So that's not going to tell us much. So we're going to take a look at the maximum magnetic field in the z direction. So what we're plotting here specifically is the agreement with the exact solution, which we can just take from time 0, because what we're putting in to the simulation, the initial data, is the exact solution. And then, so that's why I'm just setting the exact, defining the exact to be the initial value. And then this expression here, all that's doing is calculating the significant digits of agreement. So this would be the same thing if we took the 2 numbers, looked at them side by side, and just counted how many digits it takes, how long do they agree with each other before they come up with something different. So this plot leaves off time 0 because this formula uses a logarithm that if we look at time 0 against itself is just going to, we're going to take the log of 0, which is a bad thing that we should avoid. And then we can see that as time progresses, it drops off. So this is inevitable. The very nature of approximating the solution means that it will never agree exactly. But we do see that it is approaching an asymptote. So the particular resolution for this simulation is a little bit under-resolved. And doing that just because exaggerating the effect of this drop off here. But like as I mentioned, this is a well-tested code. That does have good agreement with the exact solutions. So if we wanted to take this analysis further of verifying that things match, we can do what we call convergence testing, which will be where we run a simulation at several different resolutions, and we can show that they do approach some exact solution. So what I have here are instructions for an exercise using a different code test. So it's a very, very simple one-dimensional wave parameter file called the Alfvén wave. And then if we wanted to use that to do a convergence test, what we would do is we would take that parameter file and we would run it at several different resolutions. Ideally, we would use resolutions that are a power of 2 from each other. So like divide by 2, then divide by 2 again in the dx, dy, and dz. Just because that would make the formulae for a convergence simpler if we wanted to use those to quantify just how well our simulation converges. And then, looking at the quantity of interest, Bz, that's the magnetic field in the z direction, we would look at the difference between the low and medium resolutions and the medium and high resolutions, and we would be showing that as we increase the resolution, the simulation results should be showing the error in them, or the difference between those two resolutions, should be decreasing exponentially. And then if we do that, we also need to be very careful when we try to subtract those results against each other. Because we decreased the resolution, we also need to be very careful about how we do that, because each of those files are likely to have different numbers of points in space. So we want to make sure that we don't just naively subtract one array from the other. We have to make sure that we're looking at the same points in space to do this. So that's all the material I have prepared. If there's any more questions.
So, but the same point in space is present in the files where you are subtracting, you are dividing by 2, divided by 2. They should be there, right?
Yes.
You don't have to do any interpolation or anything. It's just the right value in the right place, which will be in the finer and finer files, right? The output of the finer grids. Okay.
Yeah. It's not interpolation. It's mostly just like, so
picking the right value.
Yeah. So like the coarse grid, just pulling numbers out of a hat, you might have 0, 2, and then the next one down 0, 1, 2, and then the next 0, 1/2, 1, 1.5, 2. So like it's the biggest place I encountered this was like plotting things, trying to plot the convergence. So in that case, you end up subtracting one array from the other. So you need to make sure that you're ignoring the points in the higher resolutions that don't exist in the lower resolutions. That's all that is there with that warning.
Okay. And now I have, let's say, more general questions. How often this code changes? Is very stable? They introduce new thorns periodically, or this code have reached some maturity, or What do you think about this code? Do we need to really keep compiling this over and over to keep it
Um,
updated, or not really? How
so
old is the version of?
the core functionality is not likely to be changing rapidly.
Mhm.
Um, and then like specific thorns, like a draft, I don't think that's been touched in years. Um,
Okay.
I don't think that that repo certainly hasn't been pushed to since I tried to port the code. Um, and then I think researchers who would need more up-to-date versions are likely to be involved in the development themselves.
Okay.
So they'll be maintaining their own
Their own version.
versions of it in their home folders.
Mhm.
Um, and then uh,
So we don't need to maintain this very.
not really. The version I used is 2021, and you know, the examples I showed, the version's not going to make a difference to them. Like this, like the
The
binary black hole
black
merger, the
hole.
shooting black holes, those
Mhm.
aren't going to be changed by the difference between the version that I used and the most recent version. And there's also like there's continuous integration on the code, so they're making sure that it's all the older stuff is still going to match. Um,
And what people is doing with the new codes? So with what people are researching, or what people are adding to this Einstein toolkit? What is the leading edge, to put it that way,
um,
on this? What people is interested on adding?
so I'm not completely up to date on what's going on, but like the thorn that I showed for grFFE stuff,
Mhm.
giraffe, is actually contained in a folder that is called WVU thorns. So this was actually written by researchers at this university.
Mhm.
There's also folders. The GRMHD codes were written by researchers a couple years ago at, I believe, Illinois, Urbana-Champaign.
Mhm.
Um, Most of the recent developments that I've been following have been for other codes, but those aren't fully mature releases yet.
Okay. So this is the more mature general relativity numerical code,
Yeah.
or
Um,
there is another competing
so the
code?
other one that's uh, sort of close in maturity, at least, is, I believe, Spectre.
Mhm.
But that's using different and much more complicated techniques for its grids.
Mhm.
Um,
So
and
this
then,
one only uses, let's say, but I don't know if that is correct, Cartesian grids.
yes, that's
This
correct.
is this is a constraint on this code.
Yeah.
Only using Cartesian grids.
And then
It's Cartesian, or how you call it?
Cartesian.
Cartesian. Okay.
Um,
Those other grids that I remember from SAC years ago, when they have like those that you see like polar, like kind of polar coordinates, like a circular kind of grids. Those are in different codes that are not integrated in this.
mhm. So Spectre uses much more ad hoc patches.
Hmm.
Um, and then the other big one that I'm most familiar with is, yeah, Zach ATN's code, um, NURPy, numerical relativity for Python and beyond.
Okay,
Um,
yeah, that one, yeah.
yeah, so that's working on using uh, mostly polar grids.
Uh-huh.
Um, but there's also there's lots of other options. So the big thing with the problem really with these Cartesian grids is that they're extremely memory intensive.
Hmm.
Um, because if it weren't for that, I could very easily run research simulations on a consumer grade desktop.
Hmm.
Um, except, you know, the shooting black hole simulation that I showed requires dozens of gigabytes of memory. So that's the bottleneck for there. So what Zach was working on was
reducing the amount of memory,
right.
actually
So
the time, the time, the computational time.
yeah. So likely going to be not necessarily a significant improvement in runtime,
Okay.
but by decreasing, if we can decrease the memory requirements to something that can be run on a consumer grade desktop, we can use um, citizen science style distributed computing.
Okay.
Uh, so that's what his Black Holes at Home project is about.
Okay. Okay.
Um, so by eliminating that one bottleneck, we can just run on, thousands of volunteer desktops to push through simulations.
Mhm. Okay, good. What else can you do with this code? So you mentioned you show these black holes, you show this dragging. Uh, what else? What else? Let's say what else can you do with this not involving black hole?
So um, uh, the gallery has some options.
Mhm.
So at its base, it numerically integrates partial differential equations. So you know anything involving like a Poisson-like equation, wave equations. The other big application is probably neutron star stuff. So
Okay.
that's why the hydrodynamics codes were written to simulate neutron star systems. Um, so this is like a one-stop shop to simulate a binary neutron star merger. Um,
Which actually is more complex than the black
much,
because you have more variables there.
yeah,
In the neutron star, you have a real physical extension of the star, right? In addition to the spin, to the mass, what else?
yeah.
No, on a neutron star that is not in a black hole. Black
Uh,
hole is just two parameters, right? Mass and spin.
uh, Astrophysical black holes are two parameters,
Two parameters.
although they can also be charged. But yeah, with a neutron star, you're going to be looking at uh, fluid velocity, fluid pressure. We can ignore temperature because that's a derived quantity. Um, you're going to have the vector potential that you're evolving
Mhm.
because that's easier to work with than the magnetic field. And then the real bottleneck is going to be the neutron star equation of state, which is still a very active topic of research. Um, so the relativity side gets a little bit easier because we don't have to worry about singularities, but we do not we make up for that in much more complexity from the neutron star equation of state. But yeah, this is like I talked about Einstein toolkit as a part of the Cactus computational toolkit, but I don't think there's really other projects besides that using the CCTK infrastructure. So it's mostly just astrophysical stuff.
Okay. When you say yes, when you say astrophysical stuff, what do you mean? Let's say you are saying that in contrast to what?
Like ANSYS has very diverse applications across all kinds of engineering fields.
Uh-huh.
Um,
So here, Einstein toolkit is purely astrophysical. Uh, Not even cosmology is there. So it's
uh,
astrophysics.
I believe you could do cosmological stuff. I'm not familiar with any specific projects that do, but in principle, you could use the you need to write a thorn if one doesn't already exist to set up the initial data for a cosmological uh, case like the like an expanding universe
Mhm.
with various curvatures. But you could use the evolution thorns to evolve that without problem.
Hmm. Okay. Good.
But yeah, cosmologists do have a lot of other codes that they do use. So I don't know if any of them are using ETK.
No, not as far as I know. Well, not at least the people that I know in cosmology.
Right.
They never mentioned this, but okay. Okay, perfect.
Okay.
Are you done, right? Then do you have anything else?
That's material I have prepared.
Okay, perfect. Okay, with this we are closing our mini workshops, all the series for now. And we will see. We will have another, I think, in planning for October uh, uh, in deep learning. But we will see. We will see what Aldo says. What we will be planning for this. Okay, thank you very much. Thank
Okay.
you, Ari.
Yep.
And see you Monday, right? We have meeting.
Right. Meeting Monday morning.
Okay, perfect.
Bye.
Okay, bye.